the NMR really excites or causes the radiation absorption of the bonds in protons, proton bonds, hydrogen bonds. And then those hydrogen bonds behave like tiny magnets.
Okay.
So when the magnetic field is switched off, what do you think will happen?
Nothing.
If I provide energy to something, whatever receives the energy gets excited, right? When I switch off, when I take out the energy, that thing is gonna fall back to its
Original state.
lazy state. Yeah. So similar to what you learned in electromagnetic spectrum absorption and emission, but here it's based on how much energy was taken in. For example, here if you're starting with electrons in the bonds having random spin. Can you see my screen?
Yeah.
And then when you provide a magnetic field, this is when the magnetic field is zero. B naught is magnetic field. When you provide magnetic field of say 60 megahertz, they will be aligned, but they could be aligned either up or down, pointing up or pointing down.
Okay.
Now, depending on the power you're applying, you have different types of NMRs. You have, like they're showing here, 60 megahertz. There's also 700 megahertz. So the stronger the magnet is, the bigger the difference in energy between the two possible spins of the electrons in a bond. So first of all, know that the electrons in a bond, they are, and I'm talking about electrons onto a hydrogen, they usually can point up or down, okay? And so if they're pointing, they usually can point randomly. They can be pointing out randomly if there is no external magnetic field applied. But once you apply a magnetic field, their population is going to be split into two. Usually half the population is going to point up, half the population is going to point down in terms of spin. Now, depending on the strength of the magnet, the energy gap can be even bigger. Now, if you turn off the magnet, what happens?
They go back to their lazy state.
They go back to the original state, and the original state is usually the low energy state. That difference in energy is what is gonna give us the spectrum. It's gonna give us this spectrum because this spectrum goes with what we call frequency.
Okay.
And you know Planck's constant E equals to hv. I told you it's more of physics than chemistry here.
Okay.
So if you know the energy difference that was lost, we call it relaxation. When the spin relaxes to its original state, it's called relaxation. There's energy given out. There's an energy difference, delta E. That relates to frequency. So the NMR plots the graph based on the frequency.
Okay.
Okay?
Yeah.
So this x-axis, the frequency, the numbers we are using here, they are in parts per million because they tend to be very low numbers. Okay, so these are parts per million. So basically, these 7 here could read 7 times 10 to the power minus 6.
Okay.
So instead of those using the tiny numbers, we just say parts per million. Now, based on the environment of the hydrogen, if the hydrogen is on an oxygen, if the hydrogen is on a carbon and the carbon has an oxygen, if the hydrogen is sitting here, based on the environment, you will have these proton bonds responding differently to the magnetic field. Basically, what I'm saying is this delta E is going to be different.
Okay, depending on what the hydrogen is attached to.
Yeah, exactly. Okay.
What is that? Is it like the delta E? What is that called? Just like bond
That's
energy?
just a change in energy. It's not bond energy. It's just change in energy. Difference between the excited, the difference between the two magnetic spins. We call them.
Okay.
So we call that energy, the energy difference. that energy is between spins and is proportional to the applied magnetic field, which is what I'm talking about. And it will change depending on the environment of the hydrogen. But the stronger the magnet you have, then the better the resolution, and therefore you're going to have very taller peaks than when you're using a tiny magnet. The magnet is in this rocket-looking thing.
Okay.
Usually protected by nitrogen and helium because it does a lot of work. It gets heated so much. Every week, usually Thursdays, the lab tech always adds nitrogen, liquid nitrogen there every week. There's helium. Ideally, we should use helium, but helium is very expensive. It's a rare gas. It's difficult to get it.
Okay.
So there's a helium jacket surrounding the magnet, but bulk of the space is surrounded by the magnet, surrounded by liquid nitrogen. You know, it's freezing like negative 78 degrees.
Okay.
To keep the magnet cold. Just to answer you, the delta E is just the difference between the two states of possible spin of an electron when magnetic field is applied to the molecule.
Okay.
Yeah, so there are different solvents we use. Usually the solvent we use, we don't want them to have hydrogens. Do you know why?
Because isn't that what we're measuring?
Because you're trying to measure the hydrogens in your sample. So the solvents, they have the hydrogens replaced by deuterium, the isotope deuterium. So these are deuterated solvents. The most common one that people use is this chloroform D, but now it's a controlled substance since last year. Depending on your solubility of your sample, you can choose one of these to run your NMR. So you put your sample in a tube, and the tiny tube, capillary tube with your tiny sample is put inside the magnet, and then you go to your computer and go through the process of acquiring your spectrum. So this is an example of a spectrum. Now here at 7, usually here is where you'll see the aromatic hydrogens. All these correspond to their respective delta E's.
So is this gonna be like the IR spectra where like if it's in a certain range, it's a certain thing? Like, does that make sense?
Thank you.
So it's the same thing?
Yes. And we are getting there. Thank you for being attentive. You know where I'm going. I'm trying.
No, it's making sense. They threw me into a lab where I just had to read this stuff and I've never learned it before. It was
Sorry,
awful.
I apologize on their behalf. Next time, tell them I'll tell Moses what you're doing to me, and you're gonna get in trouble.
Yeah, I'm going to.
Yeah, so note that there are multiple proton NMR signals, not just one. This is because the magnetic field is experienced differently depending on the proton nuclei, which depends on their surrounding atoms and bonds. I've explained that.
Okay.
So usually the carboxylic acid is the one that's going to be so much to the left. The farthest we're going to go is about 12 parts per million. 9, assume 9 is here. The carboxylic acid one is going to be farthest, and like you saw it in RR, it's still going to be broad because of hydrogen bonding.
Okay.
And then it's going to be followed by the aldehyde one because it's attached directly to a very positive carbon, roughly at 9, which is what you're trying to tell me. So the carboxylic acid proton, because it's next to an oxygen, then a carbon, you have dipole moments, is going to show up at parts, about 12 parts per million, 11 to 12. And it's going to be broad.
Okay.
Then this is going to be the aromatic. And then it's going to be followed by vinylic. So we call this the vinylic CH. That is sp2. And then somewhere here, vinylic is going to be in a range. We are operating with ranges here, just like IR. And then somewhere here, you probably have a carbon that has X. X here could be halogens. It could be nitrogen, could be oxygen. So this hydrogen right here, if there's an electron withdrawing group, like halogens, nitrogen, oxygen, or even sulfur, then you expect the signal to appear somewhere here, 3 to 4.5. These ones are farther away. These are farther away from electron withdrawing groups. So this side, the hydrogens are very close to electron rich elements or environment. So we say that these hydrogens are shielded. There's so much electron density. So you'll hear your teacher using the word shielded or deshielded, where there's less electron environment.
Okay. So like deshielded would mean there's less hydrogens, whereas the shielded means there's more?
No, deshielded means that the hydrogen is far away from electron withdrawing group. The hydrogen is close to electron withdrawing group. You can see that, which pulls electrons from the environment. So like these oxygens, they're pulling electrons through bond by inductive effect from the environment of the proton.
Okay.
So
oxygen is
so
deshielded.
yeah. So the proton does not experience this shield, this blanket, this jacket, this covering of electrons, which means it's exposed to the magnetic field.
Okay.
If it's exposed to the magnetic field, how much energy, magnetic energy, will it feel? More or less?
I was gonna say a lot.
A lot. Therefore, the energy delta E will be a lot. Therefore, the frequency is a lot. So it appears to bigger numbers.
Okay.
Well,
so would it
huh?
bigger?
Huh?
Would the gap be bigger between them?
Yes, between the two spins. And then here you have a lot of electrons. It's like this is you.
So like a methyl group?
Yeah, like a metal group. Like that is you. And then you have this wall of electrons. So when the magnetic field comes in, we call it B0. When it comes in, it finds electrons there, and therefore it's difficult for the magnetic field to reach you, the proton. Okay. So you are shielded. And therefore, the gap will gonna be smaller. Delta E will be smaller. You know, E is directly proportional to frequency, so the numbers will be smaller.
Okay.
Which is why you see this hydrogen here is on a carbon close to an electron withdrawing group. This one is more deshielded than this because you're sitting on sp2 carbon that is aromatic. Okay. And that's the general idea, which is why, my friend, this table.
Memorize it?
Thank you.
Okay.
But it's less numbers than IR. IR is a lot.
I thought the IRs on my exam was so easy, and a lot of people said they were hard, so
because
I knew them.
Understood.
Yeah, I thought that was the easiest part of the exam.
That Sprite was good. Thanks to Jackie. Okay, so you see, this is what I'm talking about. I'll ask you which functional group is more deshielded?
Carboxylic acid.
Followed by?
That's an aldehyde.
Oh, which functional group is the least deshielded? Ignore the TMS. TMS is just a calibration. It helps to put the numbers right after running the experiment.
Okay. What would you call that? It's not a methyl group.
These ones? Just say alkanes.
Oh, okay.
And then you see allylic is right here. Terminal alkyne is right here. Benzylic is right here. They share the same region between 2 to 3. And alpha, we talked about alpha in mass spec, is right there. So that is the idea of NMR. I don't know what to tell you.
That's it?
Yeah. So what is left is now explaining why we see, okay, we know what should be where, but now we need to explain why we see 3 fingers, 4 fingers, 2 fingers, and so on.
Yeah, this I don't understand, because we had to do that in lab, so I didn't know, because they were trying to make us use, like, multiplet, and then my TA was like, no, it's like triplets.
Multiplet is when you have more than 6.
Okay.
Like septet.
And my professor was trying to say, like, use that, and my TA was like, that's not right, don't do it. So,
yeah, no, that is wrong, because in the exam, You will not want to say multiplet. You'll lose points.
Yeah. Okay.
Can I explain this to you?
Yeah. What slide number is that?
I don't know.
5. Thank you.
Slide 5. So I want us to work on this spectrum. I'll give you a moment.
I'm ready.
As always. That's why I love you. So let's analyze the spectrum of ethyl benzene. I'm assuming my student knows what ethyl is.
Yeah.
Okay, so first of all, I usually draw the molecule, and then we have to decide how many signals are possible. That is the first part of the question. I bet you are asked how many signals expected, and then the splitting pattern. So
It was rough.
I know, but you'll be surprised how easy this should have been. So
Yeah,
I'm expecting 3 huh?
Sorry. It took me like 8 hours to do the lab. It was awful.
Wow, that's a lot.
Yeah. Anyway, sorry.
So usually the benzene ring, when it has a bunch of hydrogens, you have no choice. It's not very clear, so here we'll have to say multiplet.
Okay. Do I have to like count the little like?
Yeah, you have to, but you see how they're masked that you can't humanly do that?
Yeah.
So that's why you say multiplet.
Okay.
However, I expect generally I expect, for this one, generally I expect 3 signals. I know the multiplet comes from the word multiple. I know he has several.
Okay.
But I'll take those aromatic hydrogens as a group showing up around 7. You know why?
It's an aromatic ring.
Thank
right
you.
there. Okay.
Now, CH2 and CH3, they don't have the same chemical environment, because on the left, the CH2 sees the phenol ring. On the right, it sees the CH3. The CH3 only sees the CH2, it does not see the phenol ring. It's farther away.
Okay.
Which is why you get the 2 signals. But now, let's explain how to get these 4 and 3 fingers. So
Okay.
there's a rule called M equals to N plus 1, where N is number of neighboring hydrogens.
Okay.
I was talking to my supervisor last week, and I told him my labs don't flow like the rest of the professors, because I like to teach first before students take the experiment.
Yeah, I wish that happened to me the other day. It was awful.
Yeah, it's not easy to do that, but I go an extra mile. I do recorded videos. I switch things around until
really nice.
until it works. Yeah, because imagine just being thrown to the lab. Today's NMR lab pre-quiz. You're given a pre-quiz you have no idea about, and then you're doing it, and you have to write a report as if you learned the whole chapter. I don't think that is learning. That's not learning.
No,
So
now I'm confused. I'm more confused than I should be.
yeah, N equals to what for this? When
What's N? Wait,
N is
so
number of neighboring hydrogens.
So would it just be 3?
Yeah, because you're just looking at the carbons. This carbon has no hydrogen.
Okay.
But the CH3 has 3 hydrogens. So we'll say 3. Now, if I plug into my rule, just allow me to flow a little bit slower than usual, as if this is slow. I'm joking. So this will be 3 plus 1. What is the answer? 3 plus 1 is not 31.
4.
Thank you. In NMR language, we call this a quartet.
Okay.
And it's right there. 1, 2,
Oh my God,
3,
that's so
4.
weird.
Huh?
They were making us like look at them and be like, what is it? And I was like, I don't know how I'm supposed to know that. Okay, that makes
You should
sense.
tell yourself, I have Moses, I won't worry. But
No,
the
yeah, I was like, I can't wait to like tell Moses about my experiences.
sorry on their behalf. Now you already know the drill. I would like you to work on the CH3. Tell me N equals to what?
So would it just be 2 plus 1? Because the number.
Yeah. That's a 3. And that's what we call a triplet, and you can see the 3 fingers right there. So if I match this and call this AB, this will be my A signal, which is what will make you do, and this will be my B signal. Now, sometimes you'll be given an NMR with an S thingy. That S thingy just is called integration.
Okay.
Or an integral. I know too much NMR because doing research, I stay in that room with this machine almost the whole day. But I'll try not to go complex on you. So that is an integral, and it just counts the number of hydrogens responsible to that peak. So this one, the number of hydrogens will be 2.
Okay.
2 hydrogens created that peak.
Okay.
Created that signal, sorry. There's a difference between peak and signal.
Okay.
So for this one, the integration will be what?
Would it be 3?
Thank you.
Okay.
And you can see the relative heights. The triplet is a little bit more than the 3 hydrogens are more than the 2 hydrogens, so relative height. And the multiplet should have been higher, but because it's splitting, instead of it being so tall, it goes down because it has to maintain what we call the peak area. Look at me now, I'm going complex. So
and then
these
no.
This would be 5 hydrogens, yeah?
Okay, so I just would count around the ring.
Yeah, unless there are times where it's quite easy to see the splittings. So for example, let me say I have A here and B here just to make them different. Then these 2 protons, based on symmetry, I'm talking about a para-substituted ring, which you'll learn in electrophilic aromatic substitution. Is coming up. I keep telling you that's a big chapter.
Can't wait.
Yeah. So I expect that both of these will be doublets.
Okay.
And they will appear at different chemical shifts, different frequencies. Because for this n equals to 1, for this n equals to 1, the black one, they are different. However, these 2 will show up at the same place, integration of 2. These 2 will show up at the same place, integration of 2.
Okay.
By doublet, I mean something like this. So you'll have 2 doublets, 2 signals on the aromatic region. It will be something like this and like that.
Okay.
So it's not always a multiplet. I wanted to caution you that.
Okay.
If the ring does not have too many hydrogens, then you can see singlets, triplets, and doublets. Are we good now with the ethobenzobenzene? Ethobenzene?
Yeah.
Okay, so apart from that, let's talk about number of signals. I already told you this. It's dependent on what calls for the number of signals. Dependent on what?
The number of hydrogens?
No, that is a splitting.
Magnetic field?
No, you're overthinking.
Wait, what's the question? I need to hear it again.
No. The question is, what dictates the outcome of number of signals in a spectrum? It's the chemical environment, right?
Yeah.
Yeah, so chemical environment, chemically equivalent hydrogens will show up on the same place.
Okay.
Because they'll be magnetically equivalent. So this one, you only have one set of hydrogens, so I expect one signal. And this signal, n equals to 0, that means m equals to 1, so this will show up as a singlet.
Okay.
But where? Where will I see that singlet? Give me a region.
Like around 0 or around 1?
No, you have this an electron withdrawing group, and it's an X group, so it's 3 to 4. Yeah. Yeah, I've already started drilling you because I can't baby you. I don't do that. You know that.
Yeah.
So X is right here. You expect it to be 3 to 4.
Okay.
You already see how to apply this, right?
Yeah.
So that is just going to be one type of signal. but we're going to do more.
Got
Tell
it.
me, how many signals do you expect from this one? I don't need the chemical shifts.
Is it like a lot?
No,
Because there's just CH groups.
no. Look, you're looking for similar hydrogen environments. So this and these are similar, right?
Yeah, and then so are all the CH2s on the top.
Yeah, because this symmetry, this molecule can be cut like this. So these and these are similar. However, you have this other one here. You have a CH3 here, different from the other CH3s. I hope you can see that.
Yeah.
Call that signal number 3. So far we're expecting 3 signals. But you're not done because there's an implied hydrogen, number 4.
Yes. Yeah.
So
What does the symmetry have to do with it? Like, what does the symmetry have to do with it? Like, should I be looking for that?
it helps you to know that this is gonna show up the same chemical shift as this on the x-axis. The
Okay.
integration will be 4.
Okay.
Okay. So let me see. N for this is. Tell me, what is the value of number of neighboring hydrogens for that?
For the CH2?
Yeah.
So would it be 3? It would be 4 because there's that neighboring hydrogen.
Thank you. Therefore, M is 5. We call this a quintet. Some people call this a pentet. And you know it's deshielded, and it's going to be somewhere between 0 and 1 parts per million. So if I would trace it, that's how it's going to look like. 1, 2, 3, 4, 5. Sometimes I become a narcissist and tell students to draw the expected spectrum out of this molecule. So they will have to trace in their chemical shifts. Okay, so this one will integrate to 4 hydrogens. You know why? The 2 CH2s will show up at the same chemical shift, somewhere between 0 and 1.
Okay. Got it.
Same thing with the CH3s, the black ones. They will show up between 0 and 1. Actually very close to 0 for those ones.
Okay.
And that's going to be integrating to 6 hydrogens.
Okay,
You know,
there. Got it.
Mm-hmm.
That makes sense.
Thank you. All right. You think I'll spare you? I will not, because you came complaining. So I have to make sure you mastered this. How many signals on that one? Before we look at something else.
Is it 4?
Let's go colorful. That one is so unique. This one is unique by himself. And this one is by himself. Oops. So how did you get 4? I wonder.
I counted the oxygen.
Is oxygen a proton?
No. Okay, so only count the proton.
This is proton NMR. We do have proton NMR, fluorine NMR, boron NMR, phosphorus NMR, carbon NMR. Right now, we are talking proton. And you guys only talk about the hydrogen and carbon NMR. You don't go to boron, fluorine, nitrogen, phosphorus. That will be for masters and PhD.
Got it.
And this proton is 2D. You're not even doing 3D. There are 4 other experiments for proton NMR in 3D, where you can now decide, yeah, this is an enantiomer, this is a diastereomer. However, you're coming there, you will have a touch of it with the enantiotopic hydrogens, diastereotopic hydrogens, homotopic hydrogens. You are coming there.
Okay.
So n equals to what for this? Let me write here 3 signals expected.
Because it's just 3 plus 1, so it's 4.
No, n equals to what for this?
Oh, 0?
Thank you.
Don't count those.
M will be 1. This is gonna be a singlet at.
Okay, so I need to make sure I don't count the CH3.
You cannot neighbor yourself.
Yeah, that makes sense.
That would be crazy. Those 3 are you and your dad and mom or your family.
Okay.
If you are too far away, you are not my neighbor. The CH2 is too far away from the black CH3.
Okay.
If it's too far away, it's not a neighbor, it's just someone in the community.
Okay, so are these all 0 then?
Yes, but you tell me the chemical shift for CH3. You're allowed to cheat.
Don't cheat? Like where
You are allowed to cheat. Just go to the general spectra and tell me where that signal will show up, the singlet.
Is it just 1?
Why would it show up at 1?
No, don't listen to me. Don't listen to me. What? Hold on.
You're looking at CH onto an oxygen.
I can't find it.
Okay, I'll show you.
It's not 1 to 5 because that's the alcohol one.
I will show you, don't worry. And these people did not show you either. It's supposed to be one of these. Remember, I listed it myself. However, you are seeing it here. See that?
Oh, okay.
There's an oxygen. You have a carbon carrying a hydrogen that you are looking at.
Okay.
So it's not on the table directly, but you see it there. I can also say this is oxygen. Can even be nitrogen, can be even be sulfur, not just halogens.
Okay.
All right. So I'm trying to teach you everything at once. Then we can solidify some things later. So this is approximately 3 to 4 parts per million. You have a question on that, or you good?
No, I'm good.
Okay, so you are right. This is n equals to 0. M is n plus 1, so it's 0 plus 1 is going to be 1. That's a singlet. What's a singlet? 1 finger. And that's going to show up further up because you have, this one is alpha, but also next to an oxygen. So there's double effect. Okay. This is going to show up at approximately above 4 parts per million. Yes, the black CH3 and the purple CH2, they are on the oxygen, but the CH2 experiences one more additional electron withdrawing effect. It's an alpha plus it has an oxygen on it. There's math to this that will actually put you at about 4.5. But for now, I'm just going to tell you. I see you did not have to do the math. There's a formula for that. But just know, if you have 2 that are sharing the same electronegative element and one has a little bit extra electronegativity pool, that one's going to show up more to the left. This we said is more deshielded.
Okay.
This is going to be more deshielded than this guy. All because of carbonyl.
Okay.
Alright. And then the CH3 is alpha. If you look at your table, you will tell me where the alpha shows up. We talked about alpha cleavage before. So we expect this to be a singlet. I hope you're taking notes.
Yeah.
At chemical shift. Chemical shift is we use a signal. A sigma.
Is it 3.3 to 5?
No, it's supposed to be 2 to 2.5 or 2 to 3. Let me show you where it is. I hope it's on your general. It's right here. See it?
Yeah.
Yeah, that is here. 2 to 2.5.
Okay. Oh, okay, got it.
See? You are now somewhere 50%. You have an idea of what's going on. So now we are set to go to more difficult things. You understand how to do this? For proton NMR. Carbon NMR, there's no splitting, thank God. But you'll have to remember the chemical shift. Using a general carbon NMR spectrum, some more numbers to memorize.
Yay.
Let's talk about what's going on here. So this is the symmetry I was telling you. You are asking me what's the importance of symmetry. Symmetry just helps you to know that these protons are similar, so you expect two signals here. However, if you're looking at ethanol, these hydrogens don't have the same connection environment. How many signals do you expect?
3.
Yeah, 3. This one, multiplicity, will be, I'll wait on you.
3.
Yeah, triplet.
Uh,
3.
sorry.
The CH2 multiplicity will be.
That
You,
won't be a
huh?
quartet because
No,
3
the
plus.
oxygen, I forgot to tell you, the OH does not split it because the hydrogen on the oxygen is not in a similar element. So would usually do the carbon-carbon hydrogen splits, not carbon-oxygen hydrogen splits. So this is gonna be a triplet, quartet.
Okay.
This does not affect CH2. Neither, just memorize OH and NHS, they don't, even the aldehyde hydrogen usually, unless you have a powerful instrument, then the aldehyde hydrogen would split with other carbon hydrogens. But even the aldehyde hydrogen does not split. So this does not affect CH2, neither is it
Okay.
affected by CH2.
So then would the one for H just be 2?
The OH will be a singlet,
Yeah. Okay.
but this guy, N will be equal to 3, so M equals to 4, and therefore it will be a quartet.
Okay.
Here there's no symmetry for the hydrogens, so I expect 3 signals. Okay,
Yeah.
I think I've nailed that so much. Let's talk about difficult things. I bet here you are so confused.
Where?
These
A little bit.
terms,
I don't even know what that is.
you don't?
Like this slide?
Yeah. Anyway, I did not expect you to. The rest I would expect you to have an idea. This one I didn't. So
Okay.
this is more complex, and we're going to determine if the hydrogens are seeing the same thing by replacement test. So in other words, you are looking at the 3D environments. We call that topicity.
Okay. So that's what topicity stands for? Just 3D environment?
Yeah, different 3D environment. Now you're looking kind of. I'll explain it better once I see a good
Okay.
molecule. I think a good molecule is down here. I'll use that. But for now, look at this. On top, that's what I call this topicity. On top, this is a CH3, correct?
Yeah.
and this one sees as CH3, but they are sharing the same carbon. So I can confidently say that these are similar, if not same. Meaning,
because they're sharing the same carbon?
Because they're sharing the same carbon, and the next carbon over has the same thing. And you know, C double bond C does not rotate.
Yeah.
So both vinylic hydrogens are forced to see their CH3s 100% of time.
Okay.
Okay. Now, if you want to confirm, to take it further, replace the top hydrogen with the bromine. You'll see that. Okay. Replace the bottom hydrogen with the bromine. Whichever atom that's not a hydrogen, just do the replacement. You know that these two are the same, right? Because if I flip it like that, it gives me that.
Okay.
So that's another test to determine that those two hydrogens are the same, and they will show up the same chemical shift with the same splitting. Everything same.
Okay.
Easy enough, right?
Yeah.
Now, since those hydrogens are saying the same thing, we say that they are homotopic.
Okay.
They see the same elements in space, so they are homotopic. Homo sapiens. Homo sapiens were called Homo sapiens because they walk upright. All of them. They have the similar way of stooping and walking upright. In genetics and what? Archaeology? Human archaeology. Yeah.
Yeah.
Constitutional isomers and heterotopic. That one just tells you that you have. We'll talk about that. It's coming.
Okay.
I don't want to explain it right now because it's not very common. Let's talk about what is common. These two.
Okay.
If they are enantiomers, the nuclei are enantiotopic. Remember, when they're talking about nuclei, they're talking about protons, because the protons have nucleus. And those nuclei affect the electrons, and those electrons are affected by the magnetic field.
Okay.
So let me just use the rest of the time to explain these two. I will not go into the complex splitting patterns. Then it's gonna not just be triplet, doublet, quartet. It now becomes doublet of doublet, doublet of triplets, triplet of triplets, quartet of triplets. It just becomes so crazy. But I checked your notes, I skimmed. Your professor did not go that deep. Yay! You're lucky. You're just gonna stay with the simple splitting: singlet, doublet, quartet, multiplet.
Okay.
So you know there's a hydrogen here, correct?
Yeah.
Now suppose that I replace, so I see, call this HA, call this HB. I'm going to go two ways. I'll keep HB, but I'll put a bromine here. Okay, versus the other way. This time, I'm keeping HA and replacing HB with a bromine, or chlorine, or deuterium D, doesn't matter. What is the relationship between these two? We are still using the replacement method.
Can I just say that's homotopic?
No, we talked about stereochemistry. What is the relationship between those two? Are they diastereomers or are they enantiomers?
Enantiomers?
You are wrong. One stereochemistry is kept. One chirality here is
Oh,
kept.
because of the top one? Okay.
This is kept, these are switched. So these are diastereomers.
Okay.
And because you form diastereomers, then we say A and B are diastereo. Thank you. Nobody will explain that to you as easy like that, but that's what it is. Let me show you something else to define an enantiotopic. I hope you still see my screen. I talk a lot sometimes and forget.
No, it's good.
Okay, so now we do the replacement. Okay, first of all, have you know that since these are diastereotopic, the number of signals I expect to see, they are a lot. This CH3 will be the first signal, and then each of these will be by themselves.
Okay.
Diastereotopic hydrogens are not same. Enantiotopic hydrogens are usually taken to be the same.
Okay.
They'll give you the same chemical shift. I repeat, diastereotopic hydrogens are not usually chemically equivalent, but enantiotopic hydrogens are usually equivalent. So I expect you count them by themselves like 1, 2, even though they are sharing the same carbon. They are seeing different things. HA is seeing the OH. HB is seeing the H.
Okay.
They are different. You see, this is dash dash.
Yeah.
And that is the OH is wedge, while this HA is wedge. So those ones, they will see each other, but the other ones will see each other. So they're different. So you have 1, 2, 3, and then this is 4, and then the OH hydrogen again is 5. Then this CH3 right here cannot be the same as the other one. I expect 6 signals.
Oh my gosh. Okay.
So,
why does the CH3 on the left and like the right, why aren't they the same signal?
No, this CH3 is farther away from OH, but the CH3 on the left is closer to the OH. They are different, so count them 1, 2. The OH hydrogen is 3. The hydrogen on the alpha carbon on OH is 4. And then these two diastereotopic hydrogens, we determine they're different.
Okay.
They see different things in space on top, so topically. So you expect 6 signals.
Okay. Okay, that makes sense. So I have to just like keep looking at what's neighboring.
Thank you.
Okay.
And notice that I did not play with the hydrogens on CH3. Because that carbon is, if I put a bromine there, that carbon 6 is not chiral. So I don't need to test the CH3. If I put a bromine here on the left, is this carbon chiral?
No.
Okay. So I did not need to test that. So I tested the CH2 because I know once I put a bromine there, that carbon becomes chiral.
Okay.
And of course, I don't need to test the CH3 at the end for the same reasons. Putting a bromine there, you don't get chiral carbon.
Okay.
Which is why we are going to dwell on this here.
Okay.
If I replace HA with a bromine, I get chiral carbon. I hope you can see that. You have a hydrogen, a bromine, an ethyl, and a methyl. That is chiral.
Okay.
So I can use my test there.
So my checklist is basically look at neighboring stuff, check chirality.
Thank you. See if you replace a hydrogen at a given carbon, you get a chiral carbon, and then decide if they're enantiotopic. Then you just tell yourself, oh, these two hydrogens will just show up at the same chemical shift. No worries.
Okay. So the enantiotopic one is kind of similar to when we just say they're symmetrical.
Yes, it's similar to what we are doing up here. That's why we are counting them as a group.
Okay.
Yeah, we know that if I do the replacement method on either of these, I'm not gonna get a chiral carbon.
Got it.
Yeah. So now, if you look at these two guys, you'll see that their relationship is gonna be, this is HB. The relationship of this is gonna be enantiomers. The outcome
is the exact same.
Yeah, they're enantiomers. So, and if they're enantiomers, the conclusion is that these two we'll conclude that they have same chemical environment.
Okay.
They will show up on the same chemical shift. Huh?
This is a lot.
You see what they're saying here? Homotopic, which is what we were doing before, and then endotopic, which of course is just gonna turn out to be same reasoning as homotopic. They have the same chemical shift, so you just call them as one signal.
Okay.
But heterotopic, which are from constitution isomers, and antiotopic and stereotopic hydrogens, they have different chemical shifts, which is why I counted 6 here.
Okay.
On here, I expect how many signals? You tell me, how many signals do we expect on here?
The one you're drawing right now?
Yeah, it's the same thing. How many signals in the NMR?
Wait, I'm sorry, for which one?
This one.
Oh, okay. Is it just 2?
Mm-hmm. Because of symmetry.
Yeah.
Yet the other guy gave us 6 because of introduction of OH.
Okay.
We
So
already had a chirality, so when you already have chirality, it gets more complex than this, but for this case, because you have chirality, just looking at the CH2 and switching, we split it even further.
Got it, okay. So there's just like a lot that you have to look for to make sure you hit all the points.
Exactly. This comes with calculations, but we'll talk about this later.
Okay.
I'll want to see, I don't know if you have a practice exam. Usually I give students, depending on the strength of the magnet, the chemical shifts can be predicted.
Okay.
However, I know I've told you that when you're going further to the left, you are deshielded. We call that downfield.
Okay.
DD, deshielded downfield, going towards 12.
Okay.
When you're going towards 0,
It's just the same as shielded.
it's shielded, and we call that upfield.
Okay.
And you know you're deshielded because you're closer to electron drawing groups. You are deshielded because the CH is the proton on the carbon is deshielded because closer to electron drawing group, farther to the left. If it's farther away from electron drawing groups, then it's gonna be shielded, surrounded by so many electrons that the magnetic field does not affect it as much to give you a larger delta E.
Okay, this makes sense.
Yeah, TMS is just a calibrator. When you do the NMR, when you run it in a computer, these signals might shift. Usually they shift further to the left, by a little bit.
Okay.
So if you want to bring them back where they should be, make sure you click the 0 out down here, and a box is gonna open up. You type in 0, and then all the peaks will be corrected to go where they need to be. This is just TMS is just a calibrator. It's an impurity we add in the NMR solvent.
Okay. It's an impurity you said?
Yeah. It's an impurity. NMR will show you everything present. So this guy brings CHs that are not in your sample. So it's an impurity, but we add it so that it can help us to zero our chemical shifts.
Okay. Oh, and that's what this like little image on the side is showing.
Yeah. That's the structure of it. So don't worry, anytime you see a peak at 0, it does not interest you. That is just TMS, calibrating to 0.
Okay. Is there like a fingerprint region in this or
No. Unfortunately, everything is
important?
Thank you.
Wait, I know you said you like looked ahead. Am I gonna have to draw structures based on like the NMR on this exam?
Yes, we'll get there. But just know the basics first. Now you see they're showing here the integrals, but I told you those integrals is just the count of hydrogens. I'll talk about this more when we meet again.
Yeah. We got a lot done though. Thank God.
Yes, actually I've given you more than 70% that you should know.
Perfect.
So
and then I'll
Uh-huh.
be more prepared. I'll be more prepared. I just have 2 exams on Wednesday, so I have a lot to study for.
So when I meet you on Wednesday, they will be out of the way.
Yeah, I take them on Wednesday, so yeah, I'm done at 3, and then I have you at 6, so I should be fine.
Okay. You
Maybe
can
a little
already
hot.
see why we have 3 signals here.
Okay.
This is broad. This is slide 24.
Wait, the broadness is the length,
No, the base.
the
See?
base.
Yeah.
So the skinnier it is, the broader it is. The same like the IR, how it would like be really skinny and deep.
You know, if you are looking at the quartet, you would argue that this is broader, but it's not, because you have to look at individual fingers at the base.
Okay.
Yeah, so this is broader. And you can argue, let me say this way what you're saying. You can argue that the broader the peak is at the base, most likely you have NH or OH. That's all you need to know. OH will show up anywhere between 0 and 6. It dances anywhere, even NH. However, I told you it's not splitting, which is why it shows up at a singlet, because it's sitting on oxygen. For this one, N equals to 3, I expect M equals to 4. So it's a quartet. The number 2 you see there is a,
I was gonna say for one, like the broad one, would that just be like an OH group?
Yeah,
It's a singlet.
yeah, nobody's splitting him. No, we say no neighboring hydrogens. This one, N equals to 2, so M will be 3, and we call that a triplet. And with that information I've given you, you should be comfortable going on, only that I'll give you more details later on.